The governing equation for viscous flow through a pipe is as follows, where here our P is equal to pressure, our gamma is equal to the specific weight of the fluid, our V is equal to velocity, where the G is equal to gravity, Z is some height measured from an origin, and our H sub L is what's known as the head loss. So this equation assumes the following. You have to have uniform velocity, the flow is steady, incompressible, and fully developed. In addition, there is no shaft work, and what we mean by shaft work is something like a pump or a turbine. And finally, the fluid properties stay constant. So this H sub L, or head loss, represents the viscous effects of the system. And we have two types. We have major head loss and we have minor head loss. So the major head loss is due to the viscous effects of the pipe itself. The minor head loss is due to any fittings or curves or bends or elbows, valves, etc. So let's look at these separately, and we'll start with the major head loss. So H sub L major is equal to the friction factor, the length over the pipe divided by diameter, the velocity in the pipe squared divided by 2g, where g is gravity. And to find the friction factor, what you do is you obtain it from the Moody chart, and in order to use the Moody chart, you need the Reynolds number and the roughness factor of the pipe divided by diameter. So this expression here was obtained through dimensional analysis. However, our minor head loss cannot be determined theoretically due to flow patterns through the various components. So what we do here is we define what's known as a loss coefficient, K sub L, and that's equal to the minor head loss divided by V squared over 2G. And this H sub L minor can be expressed in terms of what is known as, we call it here, our equivalent length. So this length, our equivalent length, which I'll call E sub L, that's equal to the length of a straight pipe that would cause the same amount of head loss as our total minor head loss. So how do we find this? Well, if our H sub L minor is equal to our loss coefficient times the velocity squared over 2g, which is equal to, now we're going to write it as we saw the major head loss, the friction factor, this equivalent length divided by d times v squared over 2g. And if you notice right here, that's exactly what we have, except instead of L, we have an equivalent L. And based on that, we can define our equivalent L equal to our loss coefficient, K sub L, times D divided by the friction factor. Remember that this is not an actual length of pipe like we use in major losses, but an equivalent one that we can use for minor losses.